I am a pizza.
I am a pizza.
With extra cheese.
With extra cheese.
From tomatoes.
From tomatoes.
I want to start this video by proving a result about finitely generated modules that isn't in Dummit and Foote as far as I can tell. I want to give you some reference for this result. You can find it, for example, as proposition 2.3 in Commutative Algebra by Atiyah and MacDonald. This Commutative Algebra Atiyah and MacDonald book is a wonderful reference for a lot of the things we've been discussing recently in this course, and also some of the things that are coming up in the next few lectures. For example, this is where I learned a lot of this material for the first time, and I often find myself going back to it as a reference for algebra facts that I should know. So Atiyah and MacDonald is commutative algebra. So one of the assumptions in this statement is that R is a commutative ring with identity. And the statement is that M is a finitely generated R module if and only if M is isomorphic to a quotient of R to the n for some n greater than 0. So let's just prove both directions here. OK, let's prove the forward direction. So let's suppose that M is a finitely generated R module. So let's choose a finite generating set, A1 up through AN. So these generate M. So we can take the direct sum, the external direct sum, RA1 plus 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 RAN. This is isomorphic to R to the n. And we can define a map from R to the n to M, where we take R1, R2 up to Rn, and send it to R1 times A1, R2 plus R2 times A2 plus 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 Rn times An. This is a surjective R module homomorphism. It's surjective because A1 up through An generate M, and it's easy to check that it satisfies the things you need to satisfy in order to be an R module homomorphism. So now, by the first isomorphism theorem, we see that R to the n mod the kernel of this R module homomorphism is isomorphic to the image, M. So M is isomorphic to a quotient of R to the n. End of sentence. M is isomorphic to a quotient of R to the n. Let's do the other direction. So if we know that M is isomorphic to a quotient of R to the n for some positive integer n, then that means we have a surjective R module homomorphism from R to the n to M. Why? Because M is isomorphic to R to the n mod some submodule, and every submodule is a kernel of some R module homomorphism. So if we take the standard basis vectors E1, E2 up to En, 1, 0, 0, 0, up to 0, 0, 0, 0, 1, these generate R to the n. And it is easy to check that the image of these generators, of this generating set, under this surjective R module homomorphism must give a generating set of M. Why? I mean, this homomorphism is surjective. So you take any element in M and you write it as phi of something, then write that something as an R linear combination of E1 up through En, and now use the fact that you have a surjective R module homomorphism, and you'll see that you can write whatever element over here as an R linear combination of phi of E1 up through phi of En. All right, so it seems to me that everything in this argument goes through exactly the same way if you drop this assumption that R is commutative. I'll leave that to you to check the details. But in order to run this part of the argument at the end, we needed this nice generating set of R to the n. So this E1 up through En. And if R doesn't necessarily have a 1, it's not as clear what you're supposed to do to modify this part of the argument. So there are a lot of places in this part of the course where things are easier if you first restrict to the case where R is a commutative ring with 1. And I think trying to understand statements like this one, that's one good example. The next thing I would like to do is solve a problem from the 2017 Algebra Comprehensive Exam. This is number 7. This problem is a classic, so I want to make sure that you've seen it. It provides a really good example for lots of questions of the form. Give an example of a ring R and an R module M that has some property. All right, so what we're going to do is prove that Q is not a free Z module. Q is an abelian group, so it's definitely a Z module. So we just have to prove that it's not a free Z module. What is a free Z module? It's a Z module that has a basis. So what does it have to have? A linearly independent spanning set. So we're going to prove that Q doesn't have a Z basis by first showing that any two elements of Q are linearly dependent. So you just take two rational numbers, A over B and C over D. And if you take B times C times A over B, that clears the denominator, B. This is some integer, plus negative A times D times C over D. Clear the denominator D. You get minus AC plus AC. You get 0. So there exist ring elements R1 and R2 so that R1 dot A over B plus R2 dot C over D equals 0. This is a non-trivial linear relation as long as it's not the case that both BC and AD minus AD are 0. But in that case, well, B and D can't be 0. So for these to both be 0, we would need to have C and A being 0. But then our rational numbers are both 0, and we could just take 1 times 0 plus 1 times 0 equals 0. So no matter what two rational numbers we pick, we get a non-trivial relation among them. So this set is linearly dependent. So if you have a linearly dependent set of size 2, and you take any larger set containing it, it's still linearly dependent. So Q doesn't have a basis of size greater than or equal to 2 because it doesn't have any linearly independent sets of size greater than or equal to 2. So if Q were a free Z module, the only possibility would be that it has a basis of size 1, that there is some element in Q where you take all of the Z multiples, you take the cyclic Z module generated by this element, and you get all of Q. But any one element of Q doesn't form a spanning set. Why? Well, just look at all the things that are of the form something in Z times A over B. So N dot A over B plus all N and Z. What are you doing? You're just adding A over B to itself. In particular, there's no way to get a rational number that has a denominator bigger than B by taking integer multiples of A over B. And Q contains rational numbers with arbitrarily large denominators. So this just isn't all of Q. So there's no basis of size 1 because there's no spanning set of size 1. So there's no basis of size 1. There's no basis of size at least 2. That means that there's no basis for Q as a Z module. So Q is not a free Z module. All right, so the very last thing that I want to do on this topic is just mention some of the exercises in section 10.3 that I think you should look at. I wouldn't spend time solving these exercises before the midterm that is on Friday, February 26th. But these are important facts that you should be aware of. So you should at least look at these exercises and think about what they're saying and then what goes into the proofs of these. All right, so exercises 10 and 11, you prove something called Shor's lemma. You're proving this in the module theoretic language. So this is a statement about R modules. Shor's lemma plays a really important role in representation theory. So if you look up Shor's lemma on Wikipedia or whatever, you'll get statements about representations, but there is an equivalent way to describe what this means in the language of R modules, and that's what you're proving here. Exercises 16 and 17, we proved the Chinese remainder theorem for rings in section 7.6 of Dummit and Foote. This gives a Chinese remainder theorem for R modules. So it's very similar. You should be aware that a statement like this is out there. I would recommend, I think I already mentioned some of these exercises when we talked about direct products of finitely many R modules. If you have submodules n1 up through nk of an R module M, we talked about the direct product n1 cross n2 cross 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 nk. But just like we talked about direct products of an arbitrary collection of groups, you can form direct products and direct sums of arbitrary collections of R modules. So exercises 20 and 21 go through the basics, and 23 and 24 prove some properties of these direct products and direct sums of arbitrary collections of R modules. And the last thing I want to mention relates to what we talked about at the beginning of this lecture, exercise 27. One thing that we saw as a consequence of Theorem 6 and Corollary 7 is that if you have a free module of finite rank over a commutative ring R, R to the n and R to the m are isomorphic if and only if n equals m. That if you have a free module of finite rank over R, then the rank really is a well-defined thing. That if you have a free basis of this free module, the cardinality is determined. All of the different free bases have the same cardinality. And exercise 27 shows that something much more complicated is going on with free modules over non-commutative rings. So a free module over a non-commutative ring need not have a unique rank, which is weird, and is, I think, another good argument for first trying to really understand how the theory of R modules works when R is a commutative ring with identity.